Good afternoon, everyone. Welcome to a Ski Institute Distinguished Lecture. I am very happy to have a good friend here who I've known for many years, Michael Holst, who's a professor of mathematics and physics at the University of California, San Diego. Michael and I met a long time ago. I can't even remember where and when, but it's long ago. And when he was more involved doing finite element analysis with the finite element toolkit, and we were doing a lot of simulation and things at the time. So he's visited here a couple of times before, but it's been a while. And it took me a little while because he's so busy and he's so popular to get him here again. But I'm happy that he's here today. So he is. He directs a number of different entities. He directs the Mathematical and Computational Physics Research Group and the Mathematics and Physics Department at UCSD. He is the co-director of the Center for Computational Mathematics. He also co-directs the interdisciplinary master's and PhD program in computational science, mathematics, and engineering at UCSD. And there's a whole list of other things that he directs and is involved with, and a number of awards. So if you'd like to know more, please go to his website, and there's a lot of detail there. Today he is going to talk about some of the work he's been doing in general relativity, the mathematics and computation and physics. He wears many hats, which I think is why we get along so well, and that he wears a computational hat, a mathematics hat, a physics hat, and probably many other hats I don't know about. But please join me in welcoming Michael Holst today.
That was recorded, right? That was the best introduction I've ever had. I'm going to just play that. That's incredible. Not true, most of it, but... okay, well, yeah, it's a great pleasure to be here. As Chris mentioned, I've been here a couple times before. I think the first time there were 8 people in Chris's research group. It looked just like my group at the time. And then I came back a few years later, and there was like 30. Maybe my group was like 5 people at that point. And now it's this huge, really successful organization. So it's really exciting. And I hope we can grow something like this in San Diego. So anyway, okay, so what I'm going to talk about today is there's sort of an outline I'm just going to kind of run through the whole talk. It's going to be here all the time. I'm not going to go through everything here. I'm going to give some background on the problem I've been working on. And I'm going to try to make it sort of precise, where I write down the equations that I have been working on and why they're interesting, why people care, and what the problems are, and then very specifically what we tried to work on. And then in particular my group, my students, postdocs that worked with me, what we did, which publications what we did in those papers. And then a little bit about algorithms for this, again, the same application. So there's sort of 2 really different kinds of work I'm going to talk about. One is just a PDE system that comes up in relativity and an analysis of that system, proving theorems about that system. And I'll explain why I even looked at that, because I'm really fundamentally more of a numerical analyst than a PDE analyst. But it ended up being sort of crucial to do any work later on the numerical side. And then the second part of the work is designing good discretizations and good methods for solving those discretizations. So of these kinds of PD systems. And so I should mention that the part I'm going to talk about at the beginning that sort of sets up the problem is there's a paper here that just appeared in the AMS bulletin. It's written from a kind of a broad point of view. My co-authors were another mathematical physicist, and then I would say another sort of computational physicist who's also a data scientist, and then someone who's really plugged into the LIGO project itself. And I had been solicited by AMS for an article like this a few years ago. Originally, it was supposed to be in the notices, and when the detection was announced, well, actually, I should say I didn't really know that the detection had been seen in September until maybe December or January. And then one of my co-authors sent me an urgent email saying, we have to get this paper out immediately. I can't tell you why. And it turns out that he knew the detection was coming, or the announcement was coming. And so we quickly finished this article and then they published it in the Bulletin. And it basically gives an overview of, from the very beginning, when GR was first postulated as a theory, and what was a source of confusion about gravitational radiation from the very beginning. Even Einstein was very confused about it. And then starting in the 50s, people from sort of the math community and sort of the theoretical, or I would say the mathematical physics community, started to really look at the PDE system as a mathematical problem. And this is all sort of outlined in this article. I'm only going to say a little bit about it in this talk, but if you want to kind of understand or sort of have a quick read, big picture of the whole sort of enterprise of the modeling of gravitational waves, and then eventually how it was done numerically, and how it fits in with the actual device that was built and the detection, and why it is that people have as much confidence as they do have, people in this field have as much confidence as they do have that it was as what they say it was. That involves a lot of computational science, a lot of data science, and so it's really an interesting combination of a lot of different fields to get to the detection. Anyway, so I encourage you to look at that. And I'll be talking about some of that material, but not a lot of it. Okay, so here's again kind of the big outline, again replicated over here. Now, in talking to Professor Berzins yesterday, it's funny, we both have come to the same conclusion recently that we have trouble explaining what it is that we do and who we are and what department we're actually in and things like that. You know, in some sense, I'm speaking to the choir here because I know all of you, in some sense, being affiliated with SCI or knowing about SCI, already have talked about this and already know where you fit. And even if it's between fields, you feel quite at home in SCI and maybe at University of Utah in general. But maybe in terms of my own work, this is sort of my sort of classification of what it is that I work on and where I fit into the world of science and mathematics. So again, there's my definition of what a mathematician is. It's a very narrow definition, I know. Here's an applied mathematician. At least this is the way I think about things. And what applied mathematics is, how that's distinct from mathematical physics. Again, you may or may not agree with these definitions, but what is computational mathematics? I see that phrase used interchangeably with these other three that are written there. I think that numerical analysis was the old terminology. It became numerical mathematics at some point, and it became scientific computation, but that wasn't sexy enough, so then it became computational mathematics. So I don't really know what the correct name for that field is right now. And what is it that these people do? And again, this is a big part of my own research career has been in this field. We study, develop, analyze algorithms. And that often means proving theorems, but sometimes it means implementing them. And so I'm a big software guy. I've been writing my own codes for a very long time. And so I do a lot of that kind of work that you do here in SCI. What's our role in science? Again, you guys all know that. That's what you do here. We're the tool makers. So what's a computational scientist? Well, those are the people that use our tools, but sometimes we're computational scientists when we use our tools to help them with their problems. So these divisions in between these fields are all very blurred. Now here, maybe more to the point here of the next slides. So what areas of mathematics are involved, at least in the stuff that I work on? Well, several very distinct branches: differential equations, applied analysis. In my thinking for my problems means I'm analyzing differential equations typically. At the level of algorithms, often there's analysis of matrix systems, and algorithms for solving matrix systems involves ideas from discrete mathematics. As data science becomes more important in the whole enterprise, knowing a lot about how data science tools are, what data science tools are available and what you can use is important. And this is more or less what I describe what I work on and what fields I work in and so on. So anyway, that's kind of an orientation. Okay, and then at the very end, I'll explain in what way in a very precise, well-understood way, I'm related to Isaac Newton. And it's not just that I work on relativity a little bit, but there's a very sort of well-accepted connection between me and Isaac that I'll explain at the end. Okay, so what is general relativity? So basically, here's the Newtonian picture of gravity that we all learn in now high school, really. fact, my son understood this when he was 10 already, and it wasn't that I taught him. He watches Crash Course, these YouTube videos. He understands all this stuff already. Anyway, the Newtonian picture is you got a heavy mass, it creates a gravitational field. If you have a small mass just moving in a straight line, it eventually feels that field, and it deflects its trajectory. The trajectory is F equals ma. F is the field created by this guy. M is the mass that determines how large the field is. And this is a very, very accurate description of what's going on unless things get very massive and unless you actually pay attention to how gravitation affects time. Then this explanation that Einstein came up with was something that took into account these other aspects. So the idea here is that when you have a large mass or large concentration of energy, it actually deforms space and time. And when you have your small mass moving along in its trajectory, it actually doesn't feel any force field at all. It just continues on a straight line, but this space-time is now curved, so that straight line is what we interpret as this curved path. And I'm only drawing space deformation here, but in fact, time also gets deformed. That's one reason the equations are so complicated and why you get very strange kind of non-intuitive kind of predictions from relativity. And how this curvature actually happens is you can write in at least a very concise system of equations called the Einstein Equations, postulated in 1915. Our article talks a little bit about the controversy around whether it was really Hilbert that wrote down the equations first because he had a variational principle. He wrote down an action. If you minimize it, it actually outpops the Einstein Equations. But there's no evidence he actually had the equations written down before Einstein. So anyway, and he was very magnanimous about giving Einstein full credit for that system. So it's an interesting history. I actually wasn't completely aware of all the details of it until we wrote that paper. So, and my physicists my physics colleagues did a lot of research on that. So anyway, so there's a system I'll write down the next couple of slides. But one of the predictions of the system, and it was realized almost immediately when the equations were written down, is that these are fundamentally wave-like equations, and they predict gravitational radiation if you have interacting masses or energies. And the waves are waves in the metric tensor. So the metric tensor is basically your distance measure. In the 3+1 Euclidean ideal Newtonian world, we have basically a very simple notion of a distance that is independent of reference frame, and we don't think about that as being something that's actually a variable or a function that could be modified in some way. So that metric tensor, which is the unknown in these equations, is basically now something that can change depending on how much matter and energy is available, and it can shorten or lengthen distances, and similarly with time in the way you measure space and time. Anyway, these are just some stolen images from the LIGO website. So there are other gravitational wave detector projects around the world. I'm just sort of showing you pictures of the LIGO project. But basically, in the late 80s, well, really, it goes back to the 60s. This is, again, described in the article a little bit. But by the late 80s, early 90s, there was enough momentum in the physics community to convince NSF to fund the construction of gravitational wave detectors. And so here are the two completed detectors, the one in Livingston, Louisiana, and the other one in Hanford, Washington. I've never seen that one, but I've flown over that one a few times. If you ever visit Pacific Northwest National Lab, you generally fly right over that one. And you can't miss it because these arms are 4 kilometers long. So anyway, so the idea was if the cosmology predictions were accurate or reasonably accurate of how many black hole collisions you would have every year, a certain radius from the Earth, it should be possible to build detectors that could detect 1 or 2 events a year or more if more sensitivity was possible. And so that was the argument that won the award from NSF. At the time it was made, it was, I think at the time already, was the single largest NSF project, if you don't count things like NCAR, which have had continuous NSF funding. And to this day, I think that the number is something like $600 million is the total cost of the project so far with various upgrades. The idea behind it is a very simple thing. It's a laser interferometer where you basically shine lasers that are a laser that's split by a prism down 2 arm lengths that are orthogonally oriented. And if you have a ripple in the space-time metric, what will happen, and these lengths are, everything is set up so that there's an interference pattern that happens. If everything is left alone, then the light that comes back is exactly canceled out. At the photodetector, you don't see anything. But if there's a ripple that comes through that changes the lengths just slightly of one of the two arms, or both maybe, then this exact or perfect cancellation doesn't happen, and you start getting pings on this photodetector. So that's basically the idea. And this is just a picture of what's called LISA, which the idea there was to put detectors in space where you could have much greater arm length distances. Basically, you don't have arms, you just have satellites that shine lasers back and forth, and you have very accurate positioning of the satellites so you know exactly how long the arm lengths are to make this kind of interferometer work in a similar way. And this is just showing how you would use special orbits to realize this kind of a detector. Okay, so anyway, I know you've all heard about this detection that was announced in February, and it was an interesting announcement because it basically was very low key. So there's going to be an update, but then they were going to have the announcement at the National Press Club. So everybody sort of figured out that it was going to be a big announcement. There was going to be a real detection announced, and basically this is what they announced at the press conference. And this first detection is described in much more detail in our article, which then, of course, just cites all of the physics articles that came out immediately after this. The first article was published sort of simultaneously. The moment the press conference started, they released the first article from the LIGO collaboration describing exactly what the detection was and what the evidence was and so on. Okay, so that's basically the setup. I haven't really written anything down, so now I'm going to write down some equations. Okay, so so the Einstein equations are basically this system right here, and well, say this system right here. And so let me just give you a good sense of what these equations are about. So basically, if you give me a vector field like a momentum vector or something like that, just a collection of functions that change with respect to some spatial variable. So v sub a would be one such guy, and I can differentiate those functions. Say they're smooth functions, I could differentiate them as much as I want, just regular calculus ideas. When we're in regular calculus, meaning the flat world, if I have functions which can be differentiated as many times as I want, they have this nice property that I could commute which order I do differentiation. So in other words, if this comma represents partial differentiation, this just means I've now taken two partial derivatives. And the index notation is just a way for me to keep track of how many partial derivatives I have. So if I start with a vector field with, say, 3 components in it, and I take a partial derivative of all 3 of those with respect to all 3, say I'm in 3 space, all 3 spatial variables, then I now have 9 functions. So that would be a 2-index object like I have here. A runs from 1 to 3, B runs from 1 to 3. So this is just a way to keep track of all 9 of those partial derivatives. So that's all this index notation is about. Something's called tensor notation or index notation. And when you're in the flat world, we know we can commute partial derivatives as long as all the derivatives are smooth functions. And so this is just an equation that represents that. If I differentiate respect to some component first and then the other, and then I change the order, I get the same thing back. Okay, but if I was actually on a smooth surface and I have to change the way I define partial differentiation, I won't explain why exactly I have to do that, but basically I want to be able to have a vector field on a surface such that when I differentiate it, I get another vector field of the same type, meaning that it really behaves like a vector field. In order to do that, I have to slightly extend what I mean by differentiation. I have to define covariant differentiation. This is one way to think about it. And what it means is basically I normally differentiate the function like I do when I'm in the flat world, but then I have to add this correction term to make sure that this thing actually does the right thing. And the right thing just basically means that it acts like a tensor or a vector field, so that if I say change the coordinate system I'm using to represent it, everything changes appropriately so that it remains sort of independent of what coordinate system I'm using to describe things with. It's kind of something you really have to be able to do if you want to be able to write down physical, mathematical equations involving physical laws that are independent of reference frame and coordinate system and so on. Okay, so if you redefine differentiation like this, so that it makes sense when you have curved surfaces like you're going to have in relativity, then you have a problem that shows up immediately, although it kind of gives us a sense of exactly what the Einstein equations is in a very simple way. But if you just do the same thing, you look at whether partial differentiation commutes, now you've got this extra piece sitting over there that doesn't vanish anymore. And so when you look at the difference between doing it one and doing the other, you're left with this extra object here that's basically a bunch of these guys. It's a bunch of these guys and some derivatives of these guys, because I have to differentiate this guy again to do this twice. Okay, and this guy is given a name. It's called the Riemann tensor. And if you actually just do the calculation, we could do it right now, given everything I have on the board here, you'll see that this is what's left over. So there's a part that just involves the second, or a derivative of this guy gamma. And then there's the part that involves the derivative of the VC, which just involves products of these gammas. Okay? And so this is a thing that if the indices all run, say, from 1 to 3, then this is a collection of 3 to the 4th functions. That's just a way of keeping track of it. But if we add some of the functions together, we can reduce the number of things we keep track of. And there are reasons to do that geometrically. This is called the Ricci tensor. Basically, there's a well-defined way to sort of raise and lower indices. I won't describe that. But basically, if we sum on some of the indices, that's the same as adding a lot of the functions together. We get a smaller guy, a smaller number of things to keep track of. And then if we sum again on these two guys, then we get just a single real number called a Riemann scalar. Okay, and so what's the Einstein equations? Well, basically, I've written it down here. It basically says that the deformation of space and time happens in response to the matter and energy density that you have. So if there's no matter or energy, the right-hand side 0, that's called the vacuum Einstein equations. And if there's matter and energy, it shows up in what's called the stress energy tensor, T. And space and time are sort of all mixed together here because the metric, the unknown thing in the system, is basically the guy that shows up in the definition of these gamma symbols. So I'll have that on the next couple of slides. Okay, so space and time are sort of all mixed together in this system. One of the very first things that people started thinking about was how can we think about this as the Cauchy problem, meaning that you slice up space and time in a way that it's filled with space-like hypersurfaces, like we normally like to think about sort of instantaneous moments in time, and then write down equations that evolve the unknown, the metric that this is an equation for, forward in time. And so this is how we understand things mathematically. We analyze Cauchy problems, evolution problems, and prove that they have solutions forward in time, locally in time, or globally in time, things like that. And so this was developed very early on, and already by the 50s, there was an initial proof by Yvon Choquet-Bruhat that the Einstein system had a well-posed initial value problem, at least locally in time. And if you want to understand how that's done, how you split this space-time system into a well-defined evolution problem that looks like this, that evolves a spatial metric forward in time, there's the first part of this well-known book by Hawking and Ellis is about this, a very condensed kind of description of how you do this. It's described in pretty much any book on general relativity will have a description of how that's done. Okay, but that said, that system that you get has been studied for really since the 50s intensively. And the system has, maybe I'll come back to this slide for a second. The system has an interesting feature that is reminiscent of what you see in the Maxwell equations. When you do this process of taking this G equals kappa T system and projecting it onto a space-like hypersurface, you get two kinds of equations. You get an evolution equation that will evolve the spatial metric forward in time. And at any moment in time, you evaluate that metric. That'll tell you how you measure space locally. But then there's another system of equations that are time independent, and they're referred to as the constraint equations. So just like in the Maxwell equations, you have a subsystem which is time independent and represents a constraint on the types of configurations that are allowed. Those are referred to as the Einstein constraint equations. Okay. Now, so I'm going to focus mainly on the constraint equations. Our paper talks a little bit about what are the interesting mathematical problems involving the evolution problem, what's known. I mentioned this result from the 50s, but this problem's been studied in greater and greater generality over the last 60 years. And there's active research on just the evolution problem, and it's one of the most active areas in mathematical physics, and there's yearly workshops and so on. So, and the same can be said about the constraint equations. It's a very interesting kind of active sort of research effort on the constraint equation that sort of, starting in about 2008, sort of really got reinvigorated with some new ideas that came in, and we're kind of at what we think is the end game for understanding the Einstein constraint equations. But so here are some of the basic questions you would have about the Einstein constraint equations, just when you write down that subsystem, which we'll have on the next couple slides. Do they have solutions? Do these constraint equations have solutions? If they do, are they always unique? How smooth are the solutions? And can we derive a priori bounds? I mean, can we say, two derivatives of the solution is bounded uniformly no matter where we are in space? Things like that. That's what I mean by a priori bounds. And for doing numerical analysis, developing algorithms, can you develop a basic approximation theory, given that you have some theory about solutions existing and there being in a certain smoothness class? And if so, can you develop error estimates that maybe even drive adaptive algorithms? Can you do things in parallel? You've got a curved space-time manifold, or if you're looking at the constraints, you have a curved spatial manifold. It's a three-manifold, so a version, sort of a three-dimensional version of a two-dimensional surface that you're having to solve the equations on. What are the complexities that arise when you're trying to deal with that kind of a system? Do you even have numerical methods for systems like that? And then finally, can you prove all this mathematically, that you have algorithms which are convergent, can give you the answer in linear complexity, things like that? So those are the basic problems that we've been looking at. So let me write down the system. I'm not going to try to have too many equations on the board all the time, but just want to give you a sense of what it is that the constraint equations are. So if you just write them down using the language of g equals 8 pi t, then you get these two equations up there. I won't explain everything other than M is the space-like manifold that's sliced through your space-time manifold. For certain types of spacetimes, you can prove there always is a spatial foliation of space-like hypersurfaces. These are referred to as globally hyperbolic spacetimes, and we believe our universe is a globally hyperbolic spacetime. So we have a foliation of space-like hypersurfaces that are parameterized by a time function. And when you project the Einstein equations onto a space-like hypersurface, the remaining degrees of freedom are a spatial metric h and its time derivative, which I've written there as k. It's called the extrinsic curvature. It's like a time derivative of h. And these constraint equations basically say that h and k have to satisfy these equations on any space-like hypersurface at any moment in time. So these equations are underdetermined. They're basically, if you do an account on these functions, there are 9 functions in each of these in 3 dimensions. There are 9 functions in each of these guys, but they're symmetric. So there's actually only 6 independent functions in each h and k. So you have 12 free functions. There's only 4 equations here. This is actually, this is actually a scalar equation. This one's actually a vector equation. You can think of it as running from 1 to 3. So there's 4 equations. So you have only 4 equations for 12 degrees of freedom. And people look at different ways for how to freely specify some parts of the data for h and k and what to then determine with the constraints. And the canonical approach that has been used since the 70s is something referred to as the York conformal decomposition. In fact, the ideas go back to the 50s, but it was sort of fully developed in the early 70s. And what you get from those 2 equations, after you specify some of the data freely, you get this system here. And the system was engineered in the 70s so that you get second-order differential operators as the principal parts that look very familiar to us. So this is the Laplacian, although this is happening on a curved surface. So this is really the Laplace-Beltrami operator. And then everything else is a lower order term in phi on this first equation. So it's a semi-linear equation in phi, which is referred to as the conformal factor. And then this guy here, this is a second-order linear differential operator on this vector w. And what is this guy here? This is a symmetrized gradient plus a trace-like term. And those of you who work in mechanics will recognize this looks an awful lot like the linear elasticity operator for a homogeneous isotropic material, except that you're specifying 2 very funny-looking Lamé constants. And that's exactly what that operator is. It's kind of the limiting case of a linear elasticity operator. So you have something like linear elasticity with some low-order nonlinear coupling to this guy. And then you have a semi-linear equation with a kind of a weird quadratic coupling due to the derivatives of this guy. So that's what's referred to as the conformal method equations. Again, this is just partial differentiation. These gammas that are needed to give you the covariant derivative so that you can actually do this calculus on a surface and have differential equations on the surface for vector fields and so on. These are defined in terms of this unknown metric h, or if we use the conformal method, we specify a background metric, and then the physical metric is recovered from the background metric h and the conformal factor that you solve for. So h is given. That gives you the Christoffel symbols, these guys gamma that give you covariant differentiation. And then everything else follows from, all the calculus is built from that setup. OK, so leave the equations for a while. So I mentioned this early paper by Shoke-Bruhat. It was actually her PhD thesis in the 50s. And the conformal method as an idea was actually already starting to appear in this work of Lichnerovich in the 40s. I mentioned that the conformal method itself, the way we think about it now, was actually something that came out of the early 70s. And what these papers did was write down that system, that coupled system, and then try to prove that there was a solution, either by looking at simplifications of the equations or something that made them amenable to some kind of analysis. So what I've done here is rewrite those equations, but in a way that simplifies the way they look a little bit to make it easier to talk about them, but also identifies two key terms. So this is that first equation again for phi. So it's a scalar equation, semi-linear for phi. It couples to w in some way, so w is like a forcing term. And then here's the vector equation for the vector w. And again, it has a forcing term that involves the other guy. And I've just defined these symbols so that they agree with the slide in the previous guy here. OK, so what are the terms in red? Well, these two equations are boundary conditions. And if you stare at them for a minute, you'll recognize that these are row band boundary conditions for, say, a domain M inside of our universe where we'd have to specify some boundary conditions. So people study this problem on closed manifolds. They study it on open manifolds with Euclidean, asymptotically Euclidean behavior, and different sort of asymptotic behavior. But on a domain with boundary, if you truncate the universe to a finite domain, you would put down some kind of boundary conditions that where these constants in the boundary condition are chosen to match some sort of physical model. The two constants here are just reflecting the coupling between the two equations. AW is the term that brings W back into phi's equation, and B tau, which is this guy here, is the coupling between the equation for W and the other equation. OK. So the conformal method basically says that we need to solve a nonlinear PDE system that looks like that. F is some combination of those two differential operators plus boundary conditions if they're present. And X and Y are just whatever the right function spaces are for this setup. And if we were going to do numerics and use methods like finite elements or spectral methods, we would actually think about a Newton equation in these function spaces so that we end up with a linear system we would want to solve iteratively. And then it's here at the last moment that you would then use your Galerkin method. You would just use a linear method. You would solve this linear system using a Galerkin method. Which is a little bit different if you were to do a finite difference method. You would think about discretizing the nonlinear problem, and then you'd have nonlinear discrete equations, and then you would use Newton's method on that system. And those two processes don't always commute. This is the standard way you handle nonlinear mechanics problems, is you discretize the problem, or you do Newton's method at the function space level and discretize that linear problem. OK. And so this is now specifically about the conformal method instead of the constraints more generally, but just the conformal method itself. Once we choose that formulation of the constraints, are there solutions? Are they unique? Are they stable? Meaning you have a priori estimates of some type. Or do you get multiplicity of solutions? Do you have folds, bifurcation phenomena? How smooth is the solution space X? Can you build good approximation spaces? And then all the questions about numerical methods. OK. So now I'll just mention a couple things here, and then I'll jump to what our group has worked on. OK, so there's one case that was studied immediately, starting in '73. The case of the two equations that is, in some sense, the easiest to understand is where one of the two coupling terms is 0. And if you look back at this equation here, let's go all the way back to this one. If this term is 0, then there's no dependence on phi in this equation. You can just solve for W, plug W into this equation, and solve this guy. The equation for W is literally the linear elasticity equation, again with sort of limiting cases for Lamé constants, but it's literally the linear elasticity equation. It's well understood. Solve for W, even numerically, solve for W. And then the whole analysis of the system comes down to, can you solve the other equation? That's referred to as the constant mean curvature case, because this corresponds to having space-like slices which are constant in the mean curvature sense. So they decouple, and already by 73 there was an initial existence result by York and Neil Omuruhu, who was involved in the development of the method itself. And then a number of results were developed over 20 years, and finally Jim Eisenberg came up with the last of those results that were needed, at least for the closed manifold setting, and showed existence, uniqueness, and a couple of cases where you don't get existence, but it was well understood why. But the other case was left open for years, and it was just not understood when the equations coupled together. What can you say? In '96, Eisenberg teamed up with Vince Moncrief at Yale, and they came up with a result that said that if the coupling is extremely small, then you get a solution, and it's unique. And then all the results that followed after that were variations on this argument. If you have very small coupling, then you get a solution. And just to give you a sense of what's going on when you try to prove a theorem about those problems, about this kind of a problem, you can think about that system as being, you can think about that system as being a system that involves two equations in some vector spaces. And if you solve one and then the other, you can think about building an iteration. This is actually, we do this computationally all the time. In fact, it's even referred to as the Gummel method in semiconductor modeling, where you solve for the potentials in the holes, and then you solve for the other term in a second iteration. You iterate back and forth. So you can do that here at the mathematical level. Solve for the vector potential W, plug it in, solve for the conformal factor phi, and go back. And you can think about that as defining a fixed point iteration for one or the other variable. If we focus on phi, you can think about it as just a fixed point iteration on phi. And you can analyze these two maps, and then there's some well-known theorems from fixed point theorems from analysis that allow you to develop theorems for the conformal method. And their theorem in '96 was basically a theorem that exploited the contraction mapping theorem. And what that was is they showed that you can build this iteration into a contraction, but the way you do it is by an idea like this. Somehow you limit the derivative of your fixed point map to be something less than 1, and then you can show that you just gained a contraction. This is a very standard thing. If you solve any linear system, and the standard thing you would do if you want to develop an iterative method is you find some approximate inverse, and maybe you throw a parameter in there, alpha, that allows you to tweak the efficiency of your method, and you just write down a sequence of identities. So the solution of this problem is the same as this guy. But then you use this identity to write down an iteration, and then hopefully you've designed G alpha so that this is a convergent iteration. And a theorem, sometimes referred to as Ostrowski's theorem, is that if that derivative is less than 1, then in fact it's a contraction, and then you have the contraction mapping theorem. But at the PDE level, you're doing the same thing. It's just that these are nonlinear functions. Okay, and basically this near CMC condition that says that the coupling's weak is some condition like this. It says the derivative of the mean extrinsic curvature has to be small. And it shows up in several places in the construction of the argument. And then I mentioned in 2008, some new ideas were brought in that basically removed this requirement and basically showed that you could get existence of solutions with no restriction on the mean extrinsic curvature. That was the thing I had worked on really since 2001, and we finally figured out how to do it for a certain scenario. And David Maxwell got essentially the same result in a different scenario. So I'm going to sort of skip this part here because I want to get to some other things in the talk. Okay. So I just want to mention, just by stating what some of the papers are and what's roughly in the paper, so you can get a sense of, from 2008 onwards, what we worked on having to do with the constraints. So these papers are all about when you can solve that coupled system. So when we say without near CMC conditions or non-CMC, this is all about trying to use this alternative fixed point framework to prove there are solutions to that system with no restriction on the mean extrinsic curvature. This one here was sort of a necessary step in order to do the next step. And why look at these different scenarios? Well, the first case you look at is closed manifolds. You don't have boundaries. You don't have any of the complexity of that. This system was about, well, what if you actually model black holes? So you have these very strange looking apparent, or what are called apparent horizon boundary conditions in the interior. It affects the whole solution theory. This, in fact, is the case that's done numerically. This is what people do in these numerical simulations. They solve the constraint equations on boundaries, on domains with black hole boundary conditions. So this we viewed as a really important thing to have in the literature, at least, so that there'd be some mathematical foundation for a solution theory for that problem. What is this about? Well, the real universe, we think, is an open universe with asymptotically flat manifolded behavior at infinity. So you want to basically develop the same kind of theoretical results for the constraint equations when you have these kind of more realistic conditions at infinity. Okay, so I'm going to skip through just the technical part of that. That would be for some of the geometric analysts who are maybe in the audience who might want to know what that looks like. Another situation that comes up is in some models you actually want to worry about modeling, say, discontinuous functions as part of the model. It turns out that everything I've been talking about requires that you be able to multiply functions together in a well-defined way, things like that. And if you look at models where you're allowing discontinuities in functions, then it becomes a lot harder to analyze any of these kinds of problems. And so we looked at some techniques for dealing with that. And we're actually having to revisit it now, as it turns out, in a way that I can describe to anyone who's interested. It involves, for anyone who's here from sort of the algebra topology community, it involves using Colombo algebra. So what this was about, so I mentioned that. Actually, it was to deal with the boundaries. So I'll skip that. And then finally, this one here. Okay, so you're right. This is just the reason I mentioned each of these papers and the names in red. These were postdocs or students who worked with me. The red names are students. Anyone whose name was in purple is a postdoc. I list everybody at the end, so I won't describe them right now. Okay, so here's sort of where things are right now. And what I meant by saying that this is the theory for the conformal method is sort of reaching its end game, is that it was realized already in maybe 10 years ago that there was something very strange going on with the conformal method, in that for different settings of some of the parameters, you could demonstrate numerically that there seemed to be two solutions. So here, I'm talking about proving theorems about existence and hopefully uniqueness, and yet we have numerical evidence that says that there's some scenarios that you don't get uniqueness. So, and in our paper that showed that you could get existence of a solution for arbitrary mean extrinsic curvature didn't have any uniqueness theorem in it. And initially it was viewed as a defect in our technique, but now it's realized that that's because you generally don't have uniqueness. And what was realized already by David Maxwell in just the next year was that you could construct special situations where you could explicitly construct two different solutions to the same problem. And this is now understood to be a generic phenomena. Anytime you depart from being near constant mean curvature, you can either get no solution to that system or you can get multiple solutions. And the latest thing that our group's been working on is to try to explore this completely using numerical path following techniques, so pseudo-arc length continuation. So the stuff that Herb Keller and others pioneered way back in the 80s. So actually we're now doing numerical methods for trying to understand what the right conjectures are to try to prove on the math side. And I just mentioned a little bit about that. We have a couple of papers on doing this numerically. And the key idea is Lyapunov-Schmidt reduction. The first time I heard those words was in Herb Keller's office in the mid-90s when I first showed up at his office. Okay, so I don't have a lot of time. In fact, I pretty much only have like 5 minutes. So I just want to say a few words about the stuff we've been doing on the numerical side, because in some sense this whole sort of effort to look at this problem was initiated by me in trying to develop some numerical methods in really the late 1990s for the constraint equations. The way that came about was when I went to Caltech as a postdoc, Herb Keller was my postdoc advisor. In my first meeting with him, the first thing he said was lose the tie. And then after he told me to remove the tie, he said, I want you to go sit in Kip Thorne's relativity class. He's teaching it this year. And I've always wanted to do a project with him. And so I want you to learn relativity. I'd actually been interested in it already because I'd been exposed to Larry Smarr's group at Illinois. And I had even talked to those guys about what some of their sort of numerical problems were, needing fast solvers, things like that. So anyway, I sat in Kip Thorne's relativity course. And I quickly settled on the constraints as something one guy could work on, and without having a big team of code people or anything. And I could just work on that problem. And then it was immediately clear that there wasn't even a good solution theory. It wasn't known when there are solutions. So you can't prove theorems about there being a good approximation if you don't even know the target exists or is unique, things like that. So I started having to look at the PDE part of it right away. But I've always worked on this. And we have published papers on proving theorems about numerical methods for elliptic problems on surfaces. I've had a couple of NSF grants just to work, or sort of a sequence of NSF grants. This has been my main line of in numerical analysis, is to work on that kind of stuff. So I'll just mention a couple things. I'm actually going to maybe go through this really fast here, but basically we just have some PDE system. And you're all familiar with Petrov-Galerkin methods. The idea is I look in a subspace of my solution space, and I try to solve that problem exactly. I'm just not looking in the whole space for everything. And also, I don't make the test functions come from the whole space. I use a possible subspace in the test space. Galerkin method, of course, is where x and y are the same space, and x, h, and y, h are the same space. But for nonlinear problems, actually, it turns out that in many cases, you actually have to use two different spaces for reasons just to make the nonlinear problem well posed. Okay. And as I mentioned, at the function space level, the way we discretize is we do Newton's method pretty much in all cases because the nonlinearities generally are very complicated. And that's just, writing that down here. So, for Galerkin methods, if you have some simple properties of the terms involved, you can prove very simple error estimates. A theorem like this, when you're working in finite elements or spectral methods or something, this is sort of the very first thing you try to prove. It basically is a theorem that says the thing you compute if you solve the Galerkin equations is within a constant of being the best approximation you could have taken from that approximation space. This is called a quasi-optimal a priori error estimate. And the reason you want to do this is that your algorithm is only involved in the construction of this. Everything to the right is just a theoretical quantity that you can compute or get a bound on. M, K, and M are PDE inequalities. And this quantity over here is a classical question in approximation theory that you look up in a book. So this thing here being bounded by some interpolant, then you look up what's known about interpolation theory for that function space. Okay, so that's your go-to theorem all the time. You always want to have that theorem. Okay, so now, of course, for this problem, it's a PDE and it's on a surface. So how is it that you actually make a numerical method give you a subspace where the supports of the functions are on complicated Riemannian surfaces? And the answer is that you pretty much can't do that. So what you have to do is build some kind of a triangulation of that surface. So already you're not able to even be in this world. You're committing what's called a variational crime. So you no longer have a subspace. Maybe it's close to a subspace, but it's not one. And the test space is not a subspace either, because you're building things that don't even live on the right spatial domain. Okay, so now, what do you do about that? Well, there's a literature that goes back to the 70s on how you handle variational crimes. If you can interpret everything in terms of a perturbation on the different terms in your bilinear form that shows up when you write down your PDE problem in weak form. And already in the 70s, Gil-Strang wrote down the first and second Strang lemmas on exactly what impact that variational crime contributes to an actual error estimate. So now, can you do that here? You can do a classical variational crimes analysis for, say, solving the Laplace-Beltrami problem on a surface, and that, in fact, was done in the 80s by Gerhard Zuck. And it was a little-known paper buried in a conference proceedings that wasn't sort of rediscovered until really early 2003 or something like that. I started seeing references to it appear. But that developed into a whole field referred to now as the surface finite element method and surface finite element community. And okay, so that's not what I'm going to do here. What we tried to look at was we wanted to have a sort of a general theory for mixed formulations of problems, because mixed formulations are a very general approach to doing linear and even some types of nonlinear problems. And so I have a little bit here on what the finite element exterior calculus is about. So I'm just going to skip to the crux of this. So what we worked on, this was Ari Stern, who was a postdoc with me for a couple of years before moving to Washington University. The idea is when you take a problem like the Poisson equation, you write it in first order form, you can think about that in this way. This is a mixed formulation of a problem like the Poisson equation. I've written it more generally here. And you can write down error estimates just like you can, what I showed you a moment ago was a standard C lemma like error estimate. And you get something that looks like this. Now, what's going on in these other terms here, these characterize some properties of the spaces and their interactions with each other. And this inequality that I wrote down here is you can find in this 2010 article by Arnold, Falk, and Winther on sort of the basic sort of mathematical properties of what is now known as the finite element exterior calculus. So that's the kind of error estimate you get. And it turns out that this framework is a very good framework, a useful framework. I'll finish in about 1 minute. A useful framework for understanding variational crimes, as it turns out, in a very general way. So here's your problem. Here's your Galerkin approximation. Here's the variational crime version of your problem. You don't have a subspace anymore. And so the question is, can you do this kind of Strang variational crimes analysis within the finite element exterior calculus framework? The answer is yes. And you get something that looks a lot like what Strang saw in the classical formulation. You get some perturbation terms. And more importantly, in terms of how it impacts solving problems on surfaces, you can actually recover the entire sort of classical surface finite element error estimate literature in this framework. So that's what we showed in our sequence of papers. And we actually just, this is something we've been working on since 2012, but we just got it accepted a week ago. We actually have a similar result for parabolic and hyperbolic problems within the finite element exterior calculus that allows you to do variational crimes within that framework. So in other words, solve hyperbolic PDE problems on a surface. And I have some more literature on adaptive methods. This was a project I did with some collaborators at LSU where they actually used our constraint solver code within an evolution code. And we actually did some numerical relativity with that. And these are just some pictures from the paper. I promised that I would list the relationship I have with Newton. So it's at the end here. Okay, so if you go to the AMS Genealogy website, you can start with my name and start going back to my advisor, my advisor's advisor, and so on. And you can eventually get back to Newton and even to Tartaglia, who was one of the guys who is known for the formula for cubic roots, for fruits of a cubic. And some of these are dual advisors. You have to take the right path. But anyway, I did find that interesting. So, okay, I'll stop there. Yep.
We have a little time for questions for Michael. Yes, Carlton.
So there are numerical codes that are being used to produce the signatures that people see in LIGO.
Right.
Do you have something to say about it? It sounds suggestive that a lot of
That's a good question. So maybe the way to answer that is, do they definitely have simulations they've well understood. They've done, even if they don't have an error estimate for their methods, they've done so many sort of numerical simulations where they the usual check where you keep having the mesh spacing and see if it converges in the, if the answer starts to converge with something. They know about all the sort of the state-of-the-art techniques when you don't have theorems, how to ensure your code's reliable and so on. They do all that stuff. These are some really good people. Do they always do simulations of things where they even know there's a solution? No. I mean, we don't necessarily have an existence theorem for the evolution problem that even covers the case that was detected. I actually don't even know the answer to that question. Yeah, so that I'm not sure how that matches up, in fact. I mean, basically, the results for the evolution problem are typically in model scenarios where you have results for small data, global in time, or you have large data, local in time. And whether you have for scenarios like black holes, arbitrarily, large energetic interactions, existence globally in time, I don't think they have complete results like that. And as soon as you throw in anything like if it's a neutron star, then you have very little, because those are more complicated. Those systems are more complicated, and less is known theoretically. So, because you have MHD coupled to GR, and you have that whole complexity. So definitely they have codes. They're very confident with them producing what they think they produce. When they do see scenario like I mentioned, there's scenarios where the constraints where numerically they can see multiple solutions. This is they ran into it in a particular case, and then they explored it numerically in papers, trying to recover the whole sort of bifurcation curve numerically. It's not something that they would generically run into, but they happen to see it, and so then they explored it. And so we took that as a launching point to explore mathematically, but I don't think things like that are an obstacle for any of those codes.
Yes, Akil.
Sure. So in, I'll just point to this here. So in this paper, what David showed was that if you look at that constraint system, the coupled system, well, exactly this system, and you allow this term to be large, and one of the terms that comes in here, this AW actually has a couple terms in it. It has a W term, it has another term called sigma that's part of the data. If you don't make the various pieces of this small, then you can show that another solution emerges. And in fact, so his paper was a very special scenario, and he was able to show some limited results analytically. And then numerically, people had actually shown an actual S-shaped bifurcation curve for a certain scenario. It wasn't exactly this one. In fact, it wasn't even completely this system. It was really just this problem. They showed that you could get S-like bifurcation phenomena just by messing around with the signs of some of these terms. It's not that surprising because semilinear problems like the Bratu problem have just the wrong sign, so that their linearization admits, develops a kernel, and that's when you can get another solution curve showing up. No, well, it's basically the idea is that so you have the constraint equations. Physically, we think there should be uniqueness of solutions. The question is, can we parameterize the constraint surface in a way that is, like parameterizing a manifold, where you can move from one chart to another in a smooth way, and you don't have anything weird happen. And what's emerging from this work is that if you're on a constant mean curvature slice, then the conformal method is a really good parameterization of the initial data. You always get existence, you always get uniqueness, except for one case, which is really well understood. It's a trivial case. But as soon as and even near CMC, if you have a slice that's very close to constant mean curvature, all the same is true. But as soon as you go beyond that, and there's a very well-defined cutoff now that's starting to appear in some of the papers, that certain parameters reach a certain critical point, then suddenly you get multiplicity or no solutions showing up. And the result is that the conformal method is going to have to be tossed out as a parameterization of the initial data for anything but CMC and near CMC. And in fact, one of the research areas is to develop a different parameterization. And some of the papers that I mentioned, they're not mine, they're actually David's, David Maxwell. He has a sequence of papers where he's trying to develop a new parameterization. The particular one he's been looking at is called the drift method, but basically it's to try to develop a well-defined parameterization that doesn't have this barrier of near CMC. And some of the papers that we published to try to explore this numerically, and the one that I'm working on with David and a postdoc who's in my group right now, it does a really careful numerical bifurcation analysis of different forms of the conformal method. And it shows S-curve behavior, it shows even bifurcation-like phenomena. We have curves crossing and things like that.
Other questions for Michael? Yes, Aaron.
This might be an outlier.
No, I would say only to the extent that the more, especially now that we have detectors, the more we can have evidence that the GR is the right model for these kinds of interactions, then that's more evidence that we still have to work with GR, and we shouldn't be looking for something completely different, but somehow that is still a good model. I mean, it's exciting from the point of view that there's other evidence for GR being the right model, but this is the first evidence of this type that it predicts these kinds of things. So in that sense, it basically gives more weight to there being something important about GR that we should hold on to. I'm not a good person to ask. But one of my co-authors on that paper, probably actually Manuel Tiglio, he seems to know all sorts of things like that. So he responds to email easily. So.
All right, well, let's thank Michael for a nice talk. Thanks.